the form YZ proportional to Z to the N. Okay, and we saw last time that if we restrict to the subgroup of the symmetries generated by Xi's with Y equal to 0, then we get super translations. But we also said that, okay, we don't really care today about super translations. So we instead want to set F equal to 0 and look at what the symmetries are, which are generated by these Xi mu's with F equal to 0 and non-zero Y obeying these constraints. Okay, so this was the setup. The group, the symmetry group is infinite dimensional in this case, because what one can do to see this is to define the generators Ln and Ln bar, which obey an algebra. And this algebra can be immediately seen to be the same as the Virasoro algebra at central charge equal to 0. And in fact, one has two copies of the Virasoro algebra from these holomorphic and anti-holomorphic vector fields. Now, there is a subgroup of this infinite dimensional algebra, which is global conformal symmetries in 2 dimensions, or equivalently, the Lorentz symmetries from a bulk point of view. And perhaps just one comment is that we already see that there is some evidence that Lorentz symmetries in 4 dimensions get enhanced to an infinite number of symmetries, just like conformal symmetries in 2 dimensions. Conformal symmetry in 2 dimensions gets enhanced to Virasoro. Now, what we saw next is that if we consider the symmetry action on radiative data, so for example, on this new tensor, NZZ, one finds an expression of this form, which involves a term which is linear in N, and a term which is a shift. So it doesn't depend on N, but just depends on this on these vector fields Y. And we also saw that we can define charges whose commutators with NZZ reproduce this symmetry action. And these two types of terms we see in the symmetry action directly map onto 2 parts of the net charge Q. One of them we call the hard charge, which has to be nonlinear, so quadratic in NZZ and CZZ in order to generate this linear action. So this can be seen using the canonical commutation relations obeyed by N and C. And the other piece of the charge is called the soft charge, which has to be linear in NZZ in order for it to generate such a shift. Okay, and so the final step in establishing the equivalence between this Virasoro, well, at this point, this sort of Virasoro asymptotic symmetry of asymptotically flat spacetimes and subleading soft theorems is to notice that the soft charge is actually the same as a subleading soft graviton. And so upon imposing a matching condition, basically identifying the charge at scri plus with the charge at scri minus. So this sort of condition imposes that these charges are conserved. And taking these well, before imposing the matching condition, they were not conserved. To impose the matching condition, they become conserved. And one can look at the associated Ward identity they give rise to. So imposing that the S matrix is invariant under the symmetry is the statement that the commutator of the S matrix with the net charge is equal to 0. But using the split into a hard and a soft piece, charge conservation becomes an equation of this form, where on the left-hand side, we have the commutator of the soft charge, which can be identified with the insertion of a soft graviton. So subleading soft graviton. And in particular, using the subleading soft graviton theorem we discussed last time, can be explicitly evaluated. So this insertion of the charge is a particular integral over the sphere of this subleading soft factor. And so evaluating this left-hand side, one finds an expression of this form, which can be precisely matched with the action of the hard charge on the asymptotic states. So we hence established that the matching condition is actually sort of equivalent to the subleading soft graviton theorem, or perhaps, in fact, conversely, the subleading soft graviton theorem imposes this charge is a statement about charge conservation, where these charges are associated with this infinite dimensional symmetry. Okay, so today we're going to be discussing celestial amplitudes, but the first lecture was not in vain. What I wanted to show is that, okay, we have this infinity of charges, but one can consider a particular soft charge, namely the one evaluated for yz equal to z minus w. And I'm allowed to do this because this is just a holomorphic function of z. And let's define this operator tzz. Okay, so far I'm just evaluating the soft charge at some particular value of yz, and plugging this expression into the soft theorem then gives us an identity of the following sort. So you have the commutator of this tzz operator with the soft with the S matrix is equal to the sum over k ranging from 1 to n of hk divided by z minus zk squared plus gamma zk zk divided by z minus zk h hat k plus 1 over z minus zk dzk acting on the S matrix without this insertion. Okay, and so here I assumed, as I said, as I sort of pointed out here, for simplicity, I'm assuming that all external states, except for the soft graviton, of course, are just scalars, but the analysis can be generalized to arbitrary spin particles. Now, if you look at this expression, you might immediately recognize that this is nothing but the Ward identity of a stress tensor in a two-dimensional conformal field theory. So this funny factor, so this is the connection on the sphere, but one can work in coordinates where the sphere is flattened to a plane, in which case this term is just going to be 0. But okay, these Ward identities have been written down in conformal field theories on any backgrounds, and they take exactly the same form. I'm just saying that you may be familiar with the version of this where this term is 0, but this is just because we are working on the celestial sphere, which has some curvature. And so so this is precisely, if you look at it, it's precisely the Ward identity of the insertion of a stress tensor in a conformal field theory, with the caveat that these HK hats, which would be weights, the weights of the external operators in this would-be correlation function, in this case, are something which looks like this. So they're a half omega k d by d omega k. Okay, so they're operators. And this is a bit strange. Well, we would like to sort of make a connection between scattering in asymptotically flat spacetimes and some kind of conformal field theory living in 2 dimensions. And if one just uses the usual S matrices, which are typically computed in a basis of momentum eigenstates, one will immediately notice that these are not diagonalized by these momentum space scattering amplitudes. So for example, you can take a simple example where you take the scattering amplitude to be proportional to something like some sort of polynomial in one of the external energies. So ck omega k to the n plus other terms. And then you can see that if you act with this operator, with this hk on a polynomial in the external energies, you're not going to get back an eigen, like a number times the S matrix, right? So in other words, the S matrix expressed in the basis of momentum eigenstates, as one usually does in quantum field theory, is not an eigenstate of these operators. So what we want, this suggests that perhaps it would be nice if one found a basis of solutions to the, so here I'm restricting to scalars for simplicity, so scalar wave equation, which diagonalizes these weights hk. And one thing to notice is that when I wrote down the expression for the subleading soft factor, it involved these projections of the angular momentum operators along directions of particles, of the particles involved in the scattering process. And so naturally, one may start looking for a basis which, instead of diagonalizing momenta, as plane waves typically do, diagonalizes boosts. So the goal now becomes the following. So we want to solve the Klein-Gordon equation with functions psi, which obey the following properties. They are boost eigenstates, namely, as we'll see in a moment, I'm claiming that this means that the sum of L0 and L0 bar acting on psi delta is equal to delta times psi delta. They're scalars, I mean, which translates into the condition that sort of the difference between L0 and L0 bar acting on psi delta is equal to 0. And we also want to impose the condition that their highest weight with respect to the Lorentz group. So this would be the condition that L1 acting, that L1 and L1 bar annihilate these wave functions. So this is a both kind of picture. So here L, just to remind everyone, I flashed them at the beginning, but they are these subgroup of this big Virasoro algebra we talked about. So they are SL2C generators, which are directly related to the Lorentz generators M mu nu, which one can take to be I x mu d mu minus x mu d mu. So these can be unfolded into rotations. So 3 rotations and 3 boosts. Okay. And there is an explicit relation between, so you might have seen this before, but let me just write it down. So L0, one can take, for example, one thing one could do is to define L0 as being the sum of the rotation generator around the x3 axis plus the boost along the 3 axis. And then similarly take the raising and lowering operators to be, in this case would be J1 plus IK1 plus minus, oh, sorry, this is minus plus L. Okay, plus minus I, J2 plus I, K2 divided by 2. And similarly, for L bar, which is R such that L bar dagger R minus L. And so now we see from these expressions that L0 plus L0 bar is proportional to a boost in the 3 direction. Yeah, so we want to diagonalize this operator in a way that's consistent also with the wave equation. But for now, let's just notice that some psi obeying these conditions so this eigenvalue and this highest weight conditions is proportional to 1 over x0 plus x3 to the delta. Okay. Now, this doesn't solve the wave equation, but that can be fixed by actually realizing that there is actually a freedom in this psi delta. So any psi delta, which is of the form some function of x squared divided by x0 plus x3 to the delta, this is Lorentz invariant, okay? So won't affect this the fact that this is an the boost eigenstate, the scalar, and the highest weight state. So the fact that I'm multiplying this, there is this freedom in multiplying this wave function with this f, and ultimately this f is going to have to obey some equation dictated by the fact that this psi solves the wave equation. So unless f of x obeys some differential equation. Okay, but before I write down that differential equation, let me point out that there was no reason in picking my L0, my SL2C generators to be these particular linear combinations. One could have instead, so more generally, one could have required that psi delta diagonalizes boosts in the Q z bar direction, where I'm defining Q hat to be one. It's a spatial vector, which a unit vector, which points towards a point on the sphere, towards the point z and z bar on the celestial sphere. So in particular, I can write this as 1 z plus z bar divided by 1 plus z bar minus I z minus z bar plus 1 plus z bar, 1 minus z bar, 1 plus z bar. So this vector is null overall, which means that Q hat squared is 1, vector Q squared is equal to 1. And what does a boost in this direction is essentially, one can define a new generator in the Q direction by dotting this vector Q into the boost generators. Okay, so now this is a boost in the Q direction. And similarly construct the other Lorentz generators. Essentially, by the other two generators would be by dotting for example, boost generators into vectors which are orthogonal to this Q, right? So one can just pick a different basis for your Lorentz group and hence a different basis for your SL2C. And then with respect to these guys, an eigenstate, which also obeys the highest wave condition, is now going to be labeled not just by a point in space-time X, but also by this vector Q hat pointing towards a point on the sphere. So again, by the argument before, this is going to look something like this. So now we have Q hat z and z bar dotted into X to the delta. And of course, the case I showed before, where this guy was just x0 plus x3 corresponds to choosing Q hat to be 1, 0, 0, 1, which is indeed a vector in the 3 direction. Its spatial part is a vector pointing in the x3 direction. So everything is consistent. Okay, so now we have these guys, which are boost eigenstates, and we want to impose, finally, that psi delta solves the wave equation. Okay. And so one can now take this and plug it into that, okay? And you can do some algebra and you find, so you can check as an exercise that f, this function f of x squared obeys the following equation. So we have 4x squared double derivative of f minus 4 delta minus 2 f prime of x squared minus m squared f x squared is equal to 0. So this is a standard differential equation. It's Bessel's equation, and it has two solutions. But we want to pick the solution that's regular as x squared goes to infinity. And this essentially picks out the Bessel function of second kind, so k. So you find that psi delta of x q hat z and z bar is equal to minus x squared to the delta minus 1. Well, up to some numerical, perhaps up to some numerical x-independent constant is proportional to the following function. This multiplied by the Bessel function, delta minus 1 m squared root of x squared. Okay, so this is what was called by Pastersky, Shaw, and Strominger. I think it's 2016, a conformal primary wave function. Okay, so in the case where m is non-zero, in a moment I'm going to discuss the massless case as well by taking the massless limit of this wave function. But let me give, okay, I think it's a good point to stop if people have any questions, because in the following I'm going to give a different presentation of these solutions, which are going to be better adapted to formulating celestial amplitudes. So I'm essentially going to write down a Fourier representation for these wave functions and kind of give some physical intuition. But if there's any questions about what I've done so far, please. Yes, Max?
Yeah, so I have a naive question. So why you are changing the base of the wave function? What is the motivation for that?
The motivation is that I want to recast the S matrix as an observable which just lives on the celestial sphere, because you just saw that the symmetries of asymptotically flat spacetimes in 4 dimensions have this infinite dimensional group, subgroup of symmetries, which are basically 2 copies of Virasoro, and those symmetries act naturally on these cross sections of future Pasnal infinity or on some celestial sphere. And I just want, the first lecture was to motivate sort of, first of all, that there exists this infinite dimensional symmetry, which suggests that perhaps there is some theory which describes scattering in 4-dimensional asymptotically flat spacetimes, in particular gravity in 4-dimensional asymptotically flat spacetimes, which lives on in 2 dimensions less on these spheres. Okay, so this was the motivation. And here, as another piece of motivation, I showed that we have this bulk sort of mode of the soft graviton, subleading soft graviton, which obeys the same identity as the stress tensor in a conformal field theory, but the S matrix is not like a nice object on which the stress tensor acts diagonally. So I'm looking, essentially this was all to motivate exactly looking for a basis which actually in which these operators become diagonal. And as I'm going to show you in a moment, that's exactly this conformal primary basis I'm talking about here, and show that this guy essentially is a boost in the direction zk.
Right, but for instance, if you want to compute the scattering amplitudes with these new plane waves, I mean, with this new form for the plane waves, it looks like it's going to be a mess, right? Or not?
Well, I'm going to show, that's the point of the remaining part of the lectures. I'm going to try to show you that there are some interesting properties these amplitudes obey, and in particular, one can import some techniques from conformal field theory to constrain them. And in fact, there's a lot of symmetries which act on the celestial sphere, which constrain, in addition to just global or perhaps Virasoro symmetries, there's another class of symmetries, which is going to be the subject of tomorrow, and we're going to see how In fact, in some examples, there is very nice formulas for these celestial amplitudes. But I agree with you that in general, if you want to describe even massive, just electron positron scattering in the spaces, is going to be not super nice, but there are some examples. And so far involving mostly massless particles, but I'm going to show an example actually of a 3-point function involving a massive particle as well, which are nice.
I see. Okay, nice, thank you.
Yeah, thanks for the question. It's great. Antonio?
Hi. So I was wondering, these conformal primary wave functions, they're quite reminiscent of the conformal primary wave functions when one studies the Klein-Gordon equation in anti-de Sitter space. We also impose this
Right.
condition. Are they related by more than just having the same symmetry, maybe by some type of flat space limit or anything like that?
I'm going to go into that exactly now. That's the next. You're anticipating.
Okay.
Yeah.
Sorry.
Great, but ask again if it doesn't, if I don't answer that question. Okay. So there are no more questions at this point. So at the end of the day, as I said, we want to recast scattering in this basis, but it turns out to be more convenient to work with the Fourier version of the conformal primary wave functions. And this is, in a moment, you're going to see why this is more convenient, because typically momentum scattering S matrices are typically expressed on the basis of momentum eigenstates, and the representation of the conformal primary wave functions I'm going to write down now is going to allow you to immediately convert a momentum space scattering amplitude into this conformal primary basis. So we have, okay, let me just be precise. It's a function of, sorry, not x hat. It's a function of x, and q hat can be written, anticipate, okay, this is going to have to do with Antonio's question. It's going to be an integral over some hyperboloid. I'm going to say in a moment what that is, for some momentum p hat of g delta p hat q hat e to the I m p hat dot x. So here, let me define what the quantities are in this, what the functions are in this formula. So g delta p hat q hat, you may be familiar with from ADS CFD. So this is a bulk to boundary propagator in ADS3, which can be written in this way, the delta. So, and p hat takes the following form. So is 1 plus proportional to 1 plus y squared plus w bar, w plus w bar minus I w minus w bar 1 minus y squared w bar. Okay, so this has the property that p hat squared is equal to -1. So what are we doing here? Let me give you some intuition. So you'll see, actually, okay, let me just draw a picture first. So remember, so now I'm going to use some ideas I talked about yesterday, that if we have a scattering process in some space-time where we have massive particles coming in with moving at some velocities, we're going to get the picture which looks something like this. Okay, it's not a perfect diagram, but this and this are essentially particles of different velocities. So they're boosted relative to one another, and they cross. I was trying to show a situation where they cross. They sort of meet at r equal to 0 at t equal to 0. But of course, in more general situation, you can have them, evolve in whatever way. But you see, the problem here is that we're interested in these in the asymptotics. But in this conformal compactification I introduced yesterday, all massive particles of any asymptotic velocities, they enter and exit space-time at one point, okay, at future time like infinity or past time like infinity. So naive question is, how do we distinguish them? And the resolution lies in resolving. So resolving future time like infinity and past time like infinity. And one way to see how one can do that is by noticing that one can split Minkowski space into 4 regions. So, okay, let me just, this is a bit bad. Okay. The 4 regions you're certainly familiar with are Rindler wedges, so these are these 2 causally disconnected regions. There's also these future and past of the null cone, which go under the name of Milne universes, Milne regions. And then upon doing the split, one can sort of foliate each of these, or slice actually each of these regions with anti-de Sitter or de Sitter slices. So let's focus on the future light cone, and let's slice it as follows. So we can introduce a particular slicing, which looks something like this. So one can see that these ADS3 slices can be identified as slices of constant t squared, tau squared equal to t squared minus r squared, where the little t and r are the usual coordinates in Minkowski space. So each, in particular, let's see, in particular, as one goes up this way, one goes to tau to infinity, and these are tau equal to 0 surfaces. The null cone is a tau equal to 0 surface. And similarly, one can also describe the past of the null cone, but let's just focus for simplicity on the future. So upon doing this, one finds that or rather as tau goes to infinity, points on the corresponding ADS3 slice. Oh, let me also say that I'm also defining some coordinate rho such that rho times tau is equal to r. So now we have these ADS3 slices with coordinates, ADS3 slices of constant tau, labeled by coordinates rho, z, and z bar. So such points, just from this diagram, you can see that they correspond, they are pierced by massive. So each point on these ADS3 slices, in particular on the slice at tau goes to infinity, is pierced by some massive particle of a different velocity. So this ADS3 slicing provides a way to kind of resolve what's going on near Scri plus. So these points are in one-to-one correspondence with massive particles of momentum p hat. So you might ask, okay, but you just told me that p hat was a function of y, z, and z bar, but the relationship between rho and y is the same as between ADS in global coordinates and the Poincaré patch. So in particular, rho goes to infinity is the boundary of ADS3, but one can introduce a different coordinates where y goes to 0 is the boundary of ADS3. This is Poincaré patch. So it turns out to be convenient to work with these y, z, and z bar coordinates instead, because it's in this coordinates that this bulk to boundary propagator takes this nice form. And so now it's natural to see, or this formula for the conformal primary wave function now becomes kind of more intuitive, because what this integral of the plane wave against this bulk to boundary propagator gives us is a map between these massive particles, which appears ADS slices at some points, and a point on the boundary of ADS, right? This is what the bulk to boundary propagator does. So we have a map which takes these massive particles, sort of identifies them with points on the celestial sphere. And in this picture, the celestial sphere would be this sort of cross-section of the null column, this common boundary of these ADS slices. Okay, now I'm not going to use this much, although I have some comments about it in the lecture notes. One can do similar analysis in these Rindler wedges and slice them with the Zitter slices. And so this is related to Antonio's observation that these conformal primary solutions look exactly the same as perhaps those you'd find by working out some solutions which satisfy the conformal Casimir on DS3, for example, or ADS3, right? They're related by some analytic continuation. But at the end of the day, you're going to find solutions which look like this. Okay. So by construction, psi delta obey the following property, that under Lorentz transformations of X and sort of conformal transformations on the sphere, so letting Q hat of Z and Z bar go to Q hat of Z prime, Z bar prime, where these are conformal transformations. This wave function transforms like a primary, like a conformal primary. So dz prime, dz to the minus delta divided by 2 times psi of delta x q hat of z, z bar. So psi transforms as a global conformal primary. Okay, so this we're gonna discuss this the implications of these transformation properties for celestial amplitudes in a lot of detail tomorrow. But I think at this point we have enough. We've done enough to be in the position to define celestial amplitude. at least when there's only massive particles involved in the process. So this is going to be some function of delta k, zk, z bar k, which is a product over I running from 1 to n. So we're imagining we're scattering n massive particles. And what one has to do to put the S matrix in this basis I just discussed is to start from the usual momentum space scattering amplitude, which is a function of these external massive momenta, and integrate it against these bulk to boundary propagators. This follows from this Fourier representation of the conformal primary wave functions I just wrote down. So we take each external leg, and we integrate each of the external legs against these bulk to boundary propagators. So this is the massive case. But turns out that the massless case can be inferred from this one by just taking a massless limit. So what about massless particles? But before I say that, I think it's a good point to stop and see if there's questions. Okay. It's not hard. Perhaps I wanted to sort of tell you about the most general picture. So I started with massive particles, but the massless case could have also been guessed. We can discuss that perhaps in the discussion session or later. But since now I developed the whole formalism, we can arrive to the massless case by just taking a massless limit. So how is that massless limit defined? So we can look at these p hats of y, z, and z bar. Oh, sorry, actually I called them. Okay, it doesn't matter too much, but let me just be consistent. W and W bar. And we see, so let me see. We see that if we take so actually, we can define P as M P hat, which has the property that P hat is equal to, P squared is equal to minus M squared. Right, so this was sort of just the unit version of the, one has to normalize it by the mass. But we can see that if we take M going to 0 for fixed M divided by 2y, or equivalently, y goes to 0, then this P hat goes to Q hat, where now, P goes to Q, where now Q squared is going to be 0. Okay, and this you can also see from this this picture that in this limit of taking M going to 0 for fixed ratio of M and Y, that implies that we're taking Y to 0, and so this means that we're taking the limit when all the points actually when all particles just cross the celestial sphere directly. So it's natural to expect that in this limit we're going to obtain a massless, sort of the celestial amplitude describing the scattering of massless particles. So just take M to 0. Oh, sorry. Take M to 0 for fixed M divided by 2y. And you can actually do this calculation. In the notes, there is a formula for how this bulk to boundary propagator behaves in this limit. And at the end of the day, so after some algebra, one can show that psi delta massless, so m equal to 0, is so this integral, this bulk to boundary propagator essentially localizes onto a delta function, and one ends up to with a melon with the sort of just integral over energies over the omega to the delta minus 1 of e to the I omega q hat x, right? So the bulk to boundary propagator collapses to just the integral against the bulk to boundary propagator of a plane wave collapses to just the sort of integral transform, which is called a Mellin transform. Okay, so now there is a caveat here. If you actually go through the exercise, you're going to see that there is actually an additional contribution. The bulk to boundary propagator is not going to be just a delta function, but it's going to have another conformally covariant term, which is going to correct this formula by a term which is the so-called shadow transform of the first piece. But you can, I don't really have time to discuss that, but you can look at Ostersky and Shaw, 2017, where they argue that this shadow piece is actually linearly dependent to just the Mellin transform itself. So it's just sufficient to consider just the Mellin transform as forming a complete basis. Okay, because the shadow is linearly dependent. And also, okay, and this you can evaluate, and this also reduces to some numerical factor divided by q hat of CNZ bar dot x to the delta, which you could also have obtained by directly taking the limit, the massless limit of this position space formula I wrote here. So there's two ways of doing this calculation, but they will both agree that there is everything is consistent, and you can check that. Okay, so but now, okay, I propose the formula which recasts scattering amplitudes in momentum space as some kind of observables living on the celestial sphere. But you may now ask, well, none of this makes sense if these solutions don't form a basis for the scalar wave equation. And in fact, again, I don't have time to discuss that, but it's been studied. This problem has been studied in this paper by Ostersky and Shaw. And the upshot is that they actually do form a basis. So the answer is yes, but provided delta is constrained. So this is, again, I'm just talking about four-dimensional asymptotically flat spacetimes and these two-dimensional celestial spheres. In this case, delta is, they found that delta has to be 1 plus I lambda, where this lambda is real and positive for massive particles, and lambda is just real for massless particles. Okay, so now one comment is that it's still it's sort of funny that the dimensions of the particles, this would tell you that sort of all of the operators in your celestial would be perhaps, celestial conformal field theory would have to have dimensions taking this form, but as we'll see tomorrow, this cannot quite be the case, because we know that here we just looked at the Lorentz subgroup of Poincare. But of course, in space-time, we also have translation invariance or momentum conservation. And as we'll see tomorrow, just simply acting with translations on these celestial operators shift the dimensions to be off this sort of kind of so-called principal series. So we will discuss that in detail tomorrow, but I should say that it's kind of, there may be a different basis in which full Poincare symmetry would be made more manifest. For example, perhaps there is a basis which would just include positive integer deltas or negative integer deltas. As we'll see, that those are also very interesting because they will be associated with the soft currents of all sorts. Okay, I have, so this is I think sort of more or less complete story of the scalar case, both massive and massless. I should say that one can also construct conformal primary solutions for spinning particles, but okay, one has to keep track of all of these spin indices, but one can run the analysis for that case. And I think there's some paper by Law and Zlonikov, 2020, and some others which discuss spinning particles, and also Pastersky and Shao discusses the case of spin 1 and spin 2. In fact, tomorrow we might touch upon that a little bit, but okay, so that can be done. And finally, I have 2 minutes now. I wanted to show you that one can do this in practice. So let's see an example. So let's consider the scattering of 2 massless and 1 massive scalars. So in this case, we start, I'm just going to do it the way I sort of outlined today. How do we construct the celestial amplitude? Well, first of all, we write down, okay, 3 level. We write down the momentum space scattering amplitude, and one has to include this momentum conserving delta function. This is very important. Omega 2 Q2 minus MP. So I singled this one as the massive 1. And what, well, I just said to put this in the celestial basis, one has to do a Mellin transform on the massless legs. So 2 Mellin transforms actually on the massless legs, and integrate against the bulk to boundary propagator, this massive leg. So this is going to just be G, and then there's going to be a product I from 1 to 2 of integral from 0 to infinity d omega I to the delta I minus 1. Okay, so this accounts for the massless guys, and then we have an integral over dy. So this is just a measure on ABS3 d squared w times the bulk to boundary propagator, so y divided by y squared plus c3 minus w squared all to the delta 3 times this momentum conserving delta function. Q1 plus omega 2 Q2 minus MP. So this is P of y w bar. And now, using the parametrizations I just wrote down for massive and massless momenta, you can see that this delta function reduces into a product of 4 delta functions. You can explicitly do some of these integrals, and I don't have time to go through, but I'm going to leave you with an exercise. So if you look at the notes, I also filled, there are some steps, some intermediate steps, which I did for you. But the upshot is that at the end of the day, we find a formula which looks something like this. So we have some function of the external dimensions, as 1, 2 to the delta 1 plus delta 2 minus delta 3, 2, 3. So this Maddalena already showed how how correlation functions, so 3-point functions in conformal field theory, are completely constrained to take this form. Sorry, 2, 3, 1, 3, delta 1 plus delta 3 minus delta 2. So this is fixed. So here we also have this SL2C, global conformal symmetry, which already fixes this function. But this coefficient, it takes a very special form. So this C delta 1, delta 2, delta 3 turns out to be proportional to a beta function, Euler beta function. I'm going to define it in a moment. Delta 1, 2 plus delta 3 divided by 2, where this beta of x and y is defined to be integral from 0 to 1 of dt t to the x minus 1, 1 minus t to the y minus 1, and we define delta 1, 2 is delta 1 minus delta 2. Okay, so this comes out of the calculation. So here up to some coupling constant and some powers of m, this is the result. So this is an example of an isolation amplitude. Tomorrow, we're going to see that one can actually use the full Poincare symmetry to completely fix this coefficient. So we're going to use different method to derive the same result. So since I'm out of time, I think this is a good point to stop. And yeah, let me know if there's questions.
Thanks, Anna. Thanks for the great lecture. And somebody has questions. I think I have one. You mentioned this about the shadow term.
Yeah.
How do you fix it? I'm not. How do you fix this term? It's.
Yeah. So here, yeah. If you do the thing I suggested, namely just take the massless limit of this formula, you're going to find two terms. I'm not sure if it's obvious or not, but
Okay.
There is a formula for this G. One of them is going to be proportional to a delta function, and the other one is going to be just proportional to something like 1 over z minus wk or something like that, to some power, to the delta. It's like one of them is going to it's going to reduce to some kind of 2-point function.
Okay, I think I missed. It follows from the limit.
It follows from the limit, but
okay.
I should have written it down, because I told you that, okay, take the limit, and you're not going to arrive at this formula by taking that limit. There's going to be some this shadow contribution, but I just restricted. I'm avoiding to discuss it because it's argued in this paper that this shadow piece, and you can also see that it's not independent. It's not linearly independent. It's sort of just an integral over the sphere of this guy. It's like taking a linear sort of linear combination of this solution. And they argued that it's sufficient to consider these spaces, but of course, given there are a lot of subtleties, which perhaps we can go into later, that 2- and 3-point functions of massless particles are singular on the celestial sphere. So here I gave an example. I got such a nice result because I considered the 3-point function involving one massive particle. But if I were to do the same thing for example, 3 gluons, you're going to get something which is actually pretty singular, still conformally covariant, but singular. And perhaps working in a basis which includes the shadow term could fix that problem. But that's an open kind of sort of rearranging your basis in a different way, which makes these 2- and 3-point functions nicer looking in some cases. It's still an open problem. But okay, at this point, I think, yeah, I think we still don't know. This is one possible choice for a basis, but there may be another choice in which things become nicer, even nicer.
Okay, thank you. Is there any other question? Yes.
Hi, hello.
Hi.
Can you show again the Merlin transform, which gives the z and z bar in terms of the integral with
The
the kernel
math.
G depending on delta.
Oh, the G1 is not a Mellin. This guy?
Yes, this guy.
Mhm.
Replacing the G delta for, let's say, the Klein-Gordon field, just for simplicity, the term that we are going to obtain in brackets, taking the extremal limit, is match the three-level, three-point function that the Witten diagram from ADS-CFT in the original form computes.
Yeah, so, well, no, it's, yeah, so you're totally right that the three-point Witten diagram would just be an integral over some point in the bulk of a product of three bulk to boundary propagators, right? Taking you from. So Witten diagram is something like this.
Mm-hmm.
Schematically, so you're going to integrate over D3 PK, and then you take G delta 1 PK Z1 G delta 3 PK Z3. Okay, but it's not obvious that here you see you have to also, if you have an amplitude, for example, you may say, okay, if we have just scattering of three massive particles, just contact interaction, then you're gonna, it's not true that you're gonna get just the Witten diagram, right? Because you have this momentum conserving delta function, which actually contracts your there's three integrals, there is a 4 momentum delta function. It's a bit more complicated, and in fact, I'm not even sure if something like 2 massive and 1 massless, or 3 massive 3-point functions have been computed. Pasterski and Strominger considered in their original calculation, they did some calculation involving, okay, I forget, some combination of these, but in some limit. It turns out to be very non-trivial. I mean, in the most general case, it's pretty non-trivial. So in what way this kind of formalism is, if it would give you something like Witten diagrams in ADS, is open problem. I cannot just tell you that, okay, this selection amplitude just computes for you some class of Witten diagrams in these cases. There may be some special cases in which the calculation reduces to Witten diagram, but I'm not sure if that was your question. Well,
yes, thank you.
okay.